Okay. Hello, ladies and gentlemen. Welcome into this special edition of ME2002. It is currently 7:51 in the PM on Wednesday evening. I'm pre-recording this particular lecture because I've got to get on a plane tomorrow for a bit of a family emergency at 4 o'clock. So I'm not going to be there for your regularly scheduled lecture to deliver it live, so apologies for that. But, this sort of stuff happens. Instead, pre-recording this, so maybe I'll go for an hour or 90 minutes or so, and that'll be it for today. What we're going to cover today is our last rotating coordinate system that we're going to use to define the kinematics of particles. We've already talked about one rotating coordinate system already, and that was the normal and tangential axes. But now we're going to move on and talk about cylindrical coordinates. And you should have some exposure to cylindrical or polar coordinates with your calculus class at this point. And we're going to sort of leverage some of the things you've probably learned in calculus to sort of help us on our way with these cylindrical coordinates. So without further ado, let's just dive in on the notepad here. I guess one other announcement I should make is that I have posted a new homework. It's homework number 6, and that will be due next Tuesday at the beginning of the lecture. It'll be on normal and tangential components, and also this new topic I'm introducing, cylindrical components. So these will be just a continuation of your rotating coordinate system or curvilinear motion notes. So let's do it. Here we talk about cylindrical coordinates. Okay. So again, we're going to start by considering a particle that's in space that's moving along a known path. Okay, so here's our particle that's moving in space along this particular path here. And unlike previously when I had sort of a reference fixed frame, previously I kind of drew in an X, Y, and a Z frame. Instead, now I'm going to have just a fixed origin point out in space here, which I'll call point O. The reason why I have this sort of fixed origin space is because the polar and cylindrical coordinates rely upon some fixed origin. And this origin is fixed in space. However, the coordinate system that we're going to use is not fixed in space. Okay, so we have this origin that's out in space, and we have our particle that exists out here, P, and it's moving along this particular path. And in this particular coordinate system, what we're going to do is we're going to define the first unit vector that makes up our new coordinate system as the unit vector that's along the path between the particle and the origin. Okay, so if I thought about the path between the origin and the particle, that is sort of this path that exists here. And so the first thing that we're going to do is we're going to establish a unit vector that exists along that particular direction, and I'm actually going to put it right on the particle. And so that unit vector here is E hat R. All right. And the reason why I do this is because I can sort of leverage the fact that this position vector is along the direction that points to P from O. So when we typically think about a fixed point in space, which would be point O in this situation, and a position vector that would define our particle P from O, we would typically write this as a position vector that looks something like a position vector which locates P from O. Usually we would write something like this. And we're leveraging here the idea that this unit vector E hat R is along the direction of R, so that now we can write that the position vector R is simply the magnitude of whatever this position vector is along the unit vector that's in this general direction. And this is sort of the foundation for our polar coordinates or our cylindrical coordinates. We have some fixed point that exists out in space O. We have a unit vector that travels along the line from O to P, and that unit vector is E hat R. And we know from kind of 2D coordinates that we need 2 basis vectors to fully define a coordinate system. So here we have E hat R, and just like we did for normal and tangential axis, we need to define a unit vector that's 90 degrees from that. And so we're going to do that here now by establishing a unit vector that's 90 degrees counterclockwise from E hat R, which would be in this general direction here. And this is going to be your E hat theta. Sorry, a little bit bad handwriting there. Okay, and so this should look to you a bit like polar coordinates, okay? So if you've done this in calculus or you've talked at all about this in calculus, usually you establish polar coordinates by sort of drawing a sort of phantom x-axis here, which is horizontal with respect to this particular picture, and you talk about the rise of this particular position vector as some angle theta. And in our cylindrical coordinate system, in our going to be rotating coordinate system, which rides on this particle P, this is also something that we're going to leverage, generally this angle here, theta. Okay, so this has flavors of polar coordinates, and you have this E hat r and E hat theta now that are defining your full two-dimensional space. All right, so unit vector perpendicular E hat r is E hat theta. Okay. We would call these radial and transverse directions. I'll just refer to them as E hat r and E hat theta. Okay. We're going to sort of gloss over a little bit of the derivation of the derivative of the unit vectors. But maybe it's a little bit useful here to do it, so let's go ahead and do it. So recall, for your normal and tangential axes, that the derivative of E hat t with respect to theta, now this is your angular derivative, was E hat n. And also that the derivative of your normal with respect to the angle theta was E hat t. This was something that you learned for your n and t axes. Sorry, there should be a negative sign here. Negative E hat t. We have a very similar idea here. Okay, if our, tangential and radial coordinate system is sort of riding along our particle, and we're thinking about the angle theta that is swept out as this particle moves from one location to another. Just like we had the derivation for the n and t axes, we're going to have a similar looking relationship between the angular derivatives of these particular unit vectors as well in our polar coordinates. So a similar idea here, and that the derivative of E hat r with respect to theta is going to be my unit vector in the theta direction, and also my derivative of the unit vector E hat theta in the theta direction is the negative unit vector pointing in the radial direction. Okay. And you can sort of prove this yourself if you would like to, or you can revisit the normal and tangential notes to sort of see that. I think it's on slide 13 of the notes if you want to check that out. But ultimately, what we want to do is we want to get to a point where we can talk about time derivatives of these guys. And just like we did for normal and tangential axes, we're going to employ some chain rule tactics to figure out the time derivatives of these particular unit vectors so that then we can actually do the acceleration and velocity time derivatives appropriately. So let's move on then, and we'll say we need now time derivatives of these particular vectors. Okay, so just like we did with normal and tangential coordinates, we're going to employ the chain rule. With the idea here being that we have something like the derivative of our radial unit vector with respect to time is going to be this compound product of three things that we here, just two things actually, that we sort of know and that's easy to understand. The first is our derivative with this thing with respect to theta. So the derivative of E hat R with respect to theta, which we know is just simply E hat T. And then we also need d theta dt. This is kind of all we really need. We know this particular bit to be E hat theta. And so we could rewrite this as just this time derivative of the angular position with respect to E hat theta. Okay, and this will be a powerful tool for us, and we'll see why in just a second. So the time derivative of the radial unit vector is the change in the angle theta with respect to time. You could think of this as an angular velocity, right? The change in the angular rate with respect to time, multiplied by the position vector that sort of points in the theta direction. Similar idea for the derivative of the transverse component. So the derivative here of E hat theta with respect to time, again, is going to be this sort of compound derivative of things we already know. This will be the angular derivative of this particular piece multiplied by d theta dt. Okay, we can identify this as our negative E hat R. And so altogether, we can rewrite this as, bringing this guy out to the front, d theta dt E hat R, all this with a negative sign in front. Okay. Again, sort of a powerful tool that describes the time derivative of a rotating unit vector that happens to be on our particle, sort of moving in space with these polar coordinates. All right. There are some shorthand notations that people typically use for this, and I've sort of talked about this before. Not my favorite representation of time derivatives, but this can also be rewritten using sort of the dot notation as what is theta dot E hat theta, and this can also be rewritten as negative theta dot E hat R. All right, where the dot here is used to represent a time derivative of the angular location. Okay. Let's keep moving. And let's put some sort of physical sense to these. I think it might be helpful. All right. So here, this theta dot, d theta dt, also known as theta dot. This is sort of the rate of rotation of this coordinate system. Okay. Now, what do I mean by that? Well, if we think about our picture again, it sort of defines what our coordinate system is. Okay, here's my origin point. Here's my particle in space P. Let's say we're moving along a path that looks something like this. So here's P. All right. Now remember that we sort of like defined a phantom horizontal here at point O. We could similarly define like that phantom horizontal here at point P. And if I were thinking about what are my unit vectors on this particular point, if you want to just think about it just for a second, using my radial and transverse unit vectors, it would be, again, thinking about the line of action between O and P as something like that. I could say that continuing right through that line of action is going to be my radial unit vector E hat R. And I also have a transverse unit vector here, E hat theta. Now, it's sort of obvious to see that this particular angle here, theta, would also match that exists back at point O, here, theta. And as I move from P to, let's say, another location, if I continue or I extend this down here, I move out to location P prime. And here I have a new sort of unit vector that exists that's pointing back or piercing through point O, back to the origin there. Let's call this E hat R prime. And I still have 90 degrees counterclockwise E hat theta prime. So I've moved to a new location here, which is P prime. And if I thought about, again, the angle that exists sort of with the horizontal in E hat R, I could think about the angle here as this angle theta. Let's call this theta prime. And it would be the same angle that you would have here, which would be also theta prime. So the idea is that this coordinate system, E hat R and E hat theta, is sort of rotating to E hat R prime and E hat theta prime through the same rotation angle that you sweep through, pointing back to sort of your origin at point O. All right, it's a little bit difficult to sort of wrap your mind around that one, but that's the general idea there. All right. So my point is that the rotating coordinate system given by E hat R and E hat T sort of rotates at the same rate or has the same angular change in time that what you see here at this particular change in angle here. So the change in angle that you get when you move from P to P prime of this particular coordinate system is the same change in angle that you get near the origin as you move from P to P prime. So the rotating coordinate system given by E hat R and E hat T has same angular position change as angle theta along E hat R and E hat R prime. Okay, so that would be this sweeping is the same as this angle and this angle together. All right. Generally, the sweeping of our basically pointer from O to point P, which is like this E hat R vector, sort of like moving along this general direction. As this changes over time, it's sweeping this angle theta that exists. And the change in this angle theta over time is basically how fast I'm like rotating about point O. So I'm rotating about O, pointing this unit vector towards my point, constantly tracking where it's going. And basically the speed that I'm rotating about point O as I'm constantly pointing at point P is what we call the angular velocity, and it's defined as this d theta dt. So here, angular velocity is d theta dt, which we also call theta dot. Okay. It's also often given the Greek letter omega. This is the lowercase omega. All right, it's not W, this is omega. All right. It's sort of hard to draw. Like what's the Washington Nationals logo? That like sort of swoopy W. See if I don't know, that Washington sort of like looks like that. It's not, I don't know, goofy looking W. All right, whatever. We call it omega in this class, lowercase omega. All right, even though this is the capital O, shh, don't tell anybody. It's meant to be a lowercase O, lowercase omega. Okay, so That's all hunky-dory, and that's out of the way. So now that we have these time derivatives of these particular unit vectors, here's the time derivative of our unit vector e hat r. Here's our time derivative of our unit vector e hat theta, written in terms of like the angular velocities of our particular coordinate system. So the faster my particle moves, the larger the value of the angular velocity required to sort of keep up with where that particle is located. So now that we have these particular pieces, we can actually start looking at the derivatives of the position to get velocity and acceleration. So now we're ready. So velocity. Okay. So position obviously is given by just our typical position vector, right? It's just this magnitude of the position vector, whatever it is, in the direction of the unit vector. All right. So that's pretty obvious. You know, when we did the normal and tangential axes, we said that the tangential axis is in the direction of the velocity always. With these polar coordinates now, we have just a slight variation on that, where we're not talking about a coordinate system that's always pointed in the direction of the velocity. Here we're talking about a coordinate system that's always pointed in the direction of the position of the particle. So similar, but slight difference. So the position of the particle here is always this magnitude of the position vector in e hat r. Okay, so now then we would be ready for velocity. Okay, so our velocity vector is the time derivative of the position. We know that. And if we rewrite the position vector in terms of sort of the coordinate system here that we have above, well, let's do that. It's the time derivative of the magnitude of r along e hat r with respect to time. Okay. Here we do the product rule. So udv plus vdu. We would have the magnitude of r, so we leave the first one alone, times the derivative of the second. Plus the derivative of the first times the second. Okay. So some interesting things here. This is just the magnitude of the position vector. Okay, it's however long the distance is between O and P. Okay, whatever that value is. You know, 14. That distance between O and P, easy to find. This guy here we know already from our time derivatives of the radial unit vector above. So if we remind ourselves all the way back up here, that the time derivative of the radial unit vector is this theta dot e hat theta. We can sort of make that substitution. So let's go ahead with that. This is magnitude of r times theta dot e hat theta. Okay. And then we're going to add to this the time derivative of the magnitude of the position. Okay, so let's talk about this for just a second. Right. So I've got this position vector that locates my particle, and over time, that particle can move closer to me if I'm the origin, or it can move farther away from me, you know, if I am the origin. So over time, even if the particle is traveling along some path here, it can still be moving closer or farther away from me. So this here represents basically the change in the particle's distance away from the origin as time progresses, right? We can relabel this as common practice would be relabeling this as the time derivative of this position vector, which is generally just called r dot. So here this is the time derivative of the length r multiplied by E hat r. This is also often relabeled a little lazily, just as r. So let's put it all together now and say that the velocity in this particular coordinate system, if we happen to know the position, would be, usually we write our radial component first, r dot E hat r, that's here, plus r theta dot E hat theta. And this is the most general definition of your velocity in cylindrical components. Okay, so let's give some actual physical meaning to this. So r, this is the distance from the fixed origin O to the particle P. Okay. R dot, this is the time derivative of the position. So here it would be the rate of change of the distance between the origin O and the point P. This is the time rate of change of the distance between origin at O and particle P. Okay, baby. Okay. This change in position, as I move sort of like in and out, always is along E hat R, because we know that our position vector always points in the direction of E hat R. So always along E hat R, okay? It's the particle basically coming into and out of a line that's between me and that particle. All right. Lastly, we got this theta dot. We've already sort of talked about this. This is the angular velocity of particle P about fixed point O. Okay. Another way to think about this is, okay, here's point O. Point P is traveling on this path. And I'm sweeping through some angle over time. It's the angle delta theta. Well, the angular velocity would just be how long did it take me to sweep through that angle delta theta in some time interval delta t. So theta dot is basically how long did it take me to change my angle theta over some time interval delta t, or if you're in a differential, d theta dt. So it takes me some amount of time to sweep through this angle delta theta. However long it took me, I can normalize delta theta by that amount of time, and that gives me my angular velocity. RPMs, revolutions per minute. That's an angular velocity. Okay. There you go. It's a general idea. All right. That's velocity. So we bang that out. Let's continue now with acceleration. All right. I think the velocity terms are pretty like straightforward and easy to understand. These terms here. I think people do okay with velocity and generally can understand the physical idea of what each one of these terms actually represents, okay? So this is basically representing how much is my particle moving into and out of a line aligned with the particle in the origin. This one is a little different, but it has to do with basically the radius of a circle multiplied by the rate at which you sweep around that circle, right? So this is like the length out to my particle multiplied by the angular velocity of the object that I'm spinning. So think about like the velocity at the end of a stick that you're sweeping around yourself. This is kind of the idea that you get. It's sort of this like r omega or r theta dot. Now, when it comes to acceleration, a lot more complicated here because we're going to do some math and there are going to be some terms that emerge, and putting some physical meaning to those actual terms is somewhat difficult. So we'll do the best that we can sort of putting some physical meanings to these accelerations, but in the end, it's going to be difficult to put your mind around all these terms. But let's give it a go anyways. Okay, so here we'll remember something like acceleration is the derivative of the velocity with respect to time. I'm going to utilize my new expression for the velocity, and that is here is r dot e at r plus r dot e hat theta. Okay, so that's my general definition of the velocity that I just defined up here. Bam. Okay. So I'm now ready again for my time derivative, and I can sort of expand this a little bit and distribute my derivative here appropriately. So this is the time derivative of r dot e hat r with respect to time plus the derivative with respect to time of this whole expression here. That you see. Okay. So we can expand this as well. Okay. So here this would be. I guess we can just kind of do this in one shot. All right, I'm going to employ the product rule on this guy. So u dv plus v du. So here we have something like r dot times the derivative of e hat r with respect to time plus dr dot dt on e hat r. So it's kind of coming from like the first term. I'm going to add to this. I'm going to sort of think about this term as just one term. So this is the derivative of the first bit times the second bit plus this r theta dot times the derivative of e hat theta dt. Okay, so this is like term number 1, and this is like term number 2. So all this sort of together here. Okay. You can sort of go through all the math here, but we have this. Okay, we have a lot of these pieces of information. All right, we talked about this way back in the beginning, that this dE hat r dt, it's the time derivative of the radial unit vector. So we go all the way back up here, time derivative of the radial unit vector, theta dot e hat theta. Okay. Plus here, this interesting term. Well, this is just the second derivative of r dot. So this just becomes r double dot. Okay, easy enough. It's the second time derivative of the position. Plus, okay, things getting a little crazy here. This here is just a constant value. No, actually, that is not a constant value. We have to consider this guy. Right. Boy, this gets a little bit messy. We've got to employ our sort of chain rule again, unfortunately. It would be dr dt times theta dot e hat theta plus r d theta dot dt e hat theta. That's coming from here. And we're adding to this our last term, r theta dot. Now our derivative of e hat theta with respect to time can go all the way back up. Is here. The derivative of e hat theta with respect to time, negative theta dot e hat r. Okay. So what I want to do now is I want to gather all my e hat r terms. I want to gather all my e hat theta terms. Okay. So like here's the e hat r, here's the e hat r, here's the e hat theta, here's e hat theta, here's e hat theta. Okay. So let's gather all of the e hat r terms. First one we see here is this r double dot. Okay. Here we see the other e hat r term, which looks like a negative theta dot squared times r. So I'll write this as minus r theta dot squared. A bit crazy. Okay. Now I want my e hat theta terms. So again, here's an e hat theta term. R dot theta dot. Here's another e hat. Oh, wait, I skipped one. Here's another e hat theta term. And so that guy is going to be, this is r dot. We can recognize that. So r dot theta dot and e hat theta. So this will be plus r dot theta dot. And then our last e hat theta term over here will be r times theta double dot. Okay, so all together, we see these two terms are the same. So let's put this all together and write a nice final form for our acceleration. R double dot minus r theta dot squared e hat r. So this is all the terms in the radial direction, all the acceleration terms in the radial direction, plus here we have two of these, so I'm going to include a 2. R dot theta dot plus r theta double dot and e hat theta. This is your full acceleration equation here. Written in radial terms. So again, let's put some definitions to these. We already defined r double dot. R again is the position between the origin at O and the point P. R dot is the change in length as you move your particle. So it's the change in position between point P and point O. And your theta dot is the angular velocity of your coordinate system. So the only things we really need to define here are r double dot and r theta double dot. So here, r double dot, this is the linear acceleration of the particle along e hat r. Okay. And theta double dot is the angular acceleration of the particle P. Okay. This is also sometimes given the Greek letter alpha. Or fish, as some people like to call it, because it sort of looks like a fish. All right. Let's put a picture on here and talk about this. So we have our accelerations and we have our velocities. Let's put a picture on here now and talk about these guys. So physical meanings. Of the acceleration terms. All right. So again, let's make our picture. Here we've got point O. Over here, we've got point P. Maybe I don't want to draw it there. But we have a position vector that defines point P from point O. Okay. I'm going to do it in blue. Here's our position vector, which points at point P from point O. I know my unit vectors, E hat R and E hat theta, my radial and tangential unit vectors. I know that there's this phantom x-axis that exists here that helps me define the position R, which is theta, and I know that that angle theta is also here. Okay. Now the idea is we're rotating this particular particle about point O. It's moving along some path. I've typically drawn it as sort of like a curved path. It can be really any path. But, you know, the curved path seems to be sort of like the most common idea, right? It's moving along some curved path. Okay, now let's give some physical meanings of these accelerational terms, right? So in E hat R, we have the following. We have R double dot E hat R, all right? This here is the second time derivative of sort of the position of the particular particle, all right? So this, remember, is the acceleration of the particle along a line that is in E hat R direction. So more or less what this particular term is this is telling me at this particular snapshot in time, how much is this particle accelerating either inward or outward along E hat R? Just strictly moving in that direction or accelerating in that direction. So if you just think about like 1D particle motion for a second, you have a particle that exists in space. It can move along that axis and accelerate along that axis. You know, we talked about this for one-dimensional motion. That's what this term is basically representing, is what is the acceleration just along that linear direction, okay? So this here, this is the extensional acceleration. Okay. The other E hat R term is this other strange one, which is negative R. Negative R theta dot squared in E hat R. Okay. Now, here we are, negative R theta dot E hat R. A little bit strange to see this, but not that strange. Because if you remember back to your normal and tangential axes, you had like a normal acceleration. So an acceleration that's like pointing inwards towards the center of curvature, which is something like the velocity squared over the radius of curvature. We have some flavors of that here, okay? So this is going to be in something like meters per second. So you'll get meters squared per second squared, and this is some distant unit, okay? So this is sort of pointing towards the center of curvature and has some squared velocity term. This is very similar. There's a squared velocity term here as well. Now this is an angular velocity, so not exactly the same. Whoa. Whoa, baby. Okay, things happened. Sorry, my writing pad just kind of blew up there. Okay, so as I was saying, you have this sort of squared velocity term and you have a distance term. And that's pretty much the same idea. And we're pointing in the negative direction, meaning I'm sort of pointing inwards towards the center of curvature, what happens to be point O, right? So this here, very similar to your N and T axes, is the centripetal acceleration term. Okay, this is an acceleration term that is strictly caused by the angular velocity of this particular piece. Okay, another way that you might want to think about it is r theta dot squared could be written as something like r times theta dot, where theta dot from way back above. You know what? I'm not even going to go down that route. Let's just leave it as it is. Okay. This is the centripetal acceleration. Okay. Sort of the next accelerational term, we have to think about are terms that exist in this general theta direction. So in this sort of tangential direction, our particle we know has got some like motion, especially if it's moving along a curve. We know that it has some general motion in that sort of e hat theta direction. Okay, so the first term that we see here is this like r theta double dot e hat theta. This is more or less the angular acceleration multiplied by the radius or the distance out to that point. And so this has got flavors of like, all right, sweeping the arc length of a circle is r theta dot. Now sort of thinking about sweeping or giving an acceleration to this particular arc length would be r theta double dot. So this here is the tangential acceleration. Okay, and thought of as acceleration from angular acceleration. Okay, so if we thought about, a particle that's riding on some rotating system, if we were sort of like speed up that rotating system, we're accelerating that system. And so there's an acceleration in sort of that, if I thought about this as my velocity vector, there's an acceleration of this velocity vector moving along that circular path as I'm rotating faster and faster. So this is basically acceleration coming from changes in angular velocity. All right. And the last term is a purely mathematical term. This last strange term that we see here is 2r dot theta dot e hat theta. That is sort of the last term in our acceleration equation. This is a strange one, and you may have heard this one in the past, and it's a little bit difficult to understand. But this is the Coriolis acceleration term. Okay, this one's a bit difficult to understand, but let's say that I am Tom Brady. Yeah, right, I wish. Okay, But no, I don't wish. I like my life. But let's say I'm sitting on a merry-go-round, and I'm Tom Brady, and I'm pointed towards the center of that merry-go-round, okay? And that merry-go-round is circling me around, okay? So I'm riding on the merry-go-round, and I'm circling around, circling around, circling around, okay? And let's say that merry-go-round is going like pretty fast, all right? Now, here I am on my merry-go-round, looking at it from above, and here's Dr. Hart on the merry-go-round, okay? And this thing is sort of rotating around this general direction, sort of spinning around this general direction with an angular velocity theta dot, okay? Now let's say I have a football with me on this merry-go-round, and I'm going to throw my football right as I cross this particular point. I'm going to throw the football from where I'm standing to point O, okay? If I was not spinning around, that ball would move right towards the origin at O, okay? If I was not spinning, I threw the ball, whoosh, it's going to throw and move right towards point O, okay? However, if this thing is sort of spinning around and I think about throwing a ball right at point O, what's going to happen is it's not going to move right towards point O. It's going to move in sort of a curved path that looks something like that. Okay, so that would be like the trajectory of the ball in this particular situation. And so if I thought about putting my coordinates on myself that we sort of talked about, which would be my E hat R, and in this situation, E hat theta, we see that like the velocity vector of the particle here has got some component now that's in E hat theta. And the component that comes up from sort of this effect that couples like moving my particle generally in this direction, which would be like an R dot term, and having me stand on this rotating platform, which would be like a theta dot term, causes some amount of this vector to be in like the E hat theta direction, okay? And that amount that we have, or that amount of acceleration that occurs to cause that velocity vector to sort of move in the E hat theta direction, is this Coriolis term, 2r dot theta dot. All right. Another way I like to think about it, if you're like a football fan, is one last silly example. Here's your offensive line. I'm Tom Brady again. I got a lot of Tom Brady examples. Maybe I should be Aaron Rodgers. That would be better. Okay, but here's Aaron Rodgers. All right, he's playing on the football field. Here's the football field. All right, and he's going to roll out to the right. All right, he's got a football in his hands. Okay, so because he's sort of like traveling to the right, if he wants to hit a receiver that's sort of moving across the field this way, since he already has some velocity in this general direction, if he were to throw it straight ahead, it's going to arc off to the side because he has some inherent velocity already. Okay, so this is another sort of idea of the Coriolis effect, is that because there's already some inherent velocity in this general direction, if I were to stand here without any motion and throw it straight ahead, yeah, okay, it has this sort of straight ahead trajectory. But because I'm sort of moving to the right at the time of release of the ball, it's going to sort of trail off to the right because it already has some velocity from me sort of moving. So again, kind of another idea of this Coriolis effect. That one's a little bit more subtle, but you get the idea. Okay, a lot of football analogies today. Hope you guys watch football. American football, that is. Okay, so there you go, trying to give you some idea of the terms. All right, let's cap off this this lecture here with an example problem. So I'm going to bring an example problem here into the lecture notes, and we'll work through it. And this is an example from the notes. Okay. See if I can blow this up a little bit for you guys. Okay. So here we have the rotation of this 0.9 meter arm about O. It's defined by the relationship theta is some function of time. Okay. So here's an angle theta that we're making with the horizontal. And we're told that this shaft here, this like shaft OA, is rotating with some time function, which is 0.15 t squared. That means that it's sort of increasing its angle of theta in this general direction as a function of time. So basically this guy is just sort of moving along in this way, and its angular motion is increasing with time t squared. All right. We're also told some information about what's going on with collar B. All right. Collar B slides along the arm such a way that its distance from O to R is also given by some time function. So what this means is that as time elapses, this collar is like sliding back and forth along this particular shaft. And that is given also as a function of time here that we happen to know. All right, interesting. We want to know, after this arm has rotated through 30 degrees, we want to know the total velocity of the collar, the total acceleration of the collar, and the relative acceleration of the collar with respect to the arm. Interesting, interesting, interesting. Okay. And I can do something interesting right now. Pause the video if you would like to take some time to copy this down. Otherwise, I'm going to go right into it. So I'll give you a second if you want to pause and continue copying down. Otherwise, I'll go right into it. Okay. So we have sort of our position of this guy, and really this is going to end up being our particle. And so this is the particle or the collar that's acting at point B. So our position here is given as a function of time, both in this theta and this r. So here we have position in cylindrical components. And let's tackle part A first. We want the total velocity of the collar. Well, total velocity, maybe we can get an expression for velocity as a function of time and go about that. So we'll say here, to solve this problem for velocity and acceleration, we need many things. Specifically, if we look at our equations, we're going to need position r. We're going to need basically the change of length of this with respect to time. We're going to need the acceleration of this collar along the shaft as a function of time, which we call r double dot. We need the angular position theta. We need the angular velocity theta dot, and we need the angular acceleration theta double dot. So we'll start by sort of getting all of these things as functions of time, and then work our way through the problem, given, you know, the certain things that we're sort of looking for. Okay. So as a function of time, we kind of have the following. That our position r is given. So what is this total distance between O and our collar at B? Well, that's given here. 0.9 minus 0.12 t squared. Okay. I'm going to just work through these time derivatives here. So I want, how much is this thing changing its position, or what is its velocity along the collar? Well, that's just the first derivative of that, which is going to be 0.24 t. And the second derivative with respect to time here is going to be negative 0.24. Right. If we want, we should probably put some units on this. We're told that this is in meters for t in seconds. So that's important to know. After we take the first derivative, we'll have something like meters per second if t is in seconds. And here we'll have something like meters per second squared for units. So good for us to sort of keep the units straight in our head. All right. Now, another thing that we have is we have a function that describes what is the angle theta as a function of time. And in this particular example, we're going to need some times to sort of plug in to determine exactly what my value of r dot, and r double dot are. And so this particular problem, we're interested in theta is 30 degrees, which in radians, pi on 6. Usually talk in radians when you're doing these like radial tangential sort of problems. Okay, and we also have an expression for theta as a function of time. We know that theta is here, where theta is expressed in radians and t is in seconds. Okay, so 0.15 t squared. Okay, and this is radians for t in seconds. Okay, so what I can do with this information is I can actually figure out how long it takes our object to get to our theta equals 30 degrees, and then figure out what is the specific snapshot in time that I'm interested in this problem. So solve for t. And if you do this, you'll find that the only t that makes sense, you could have plus or minus here, but negative time doesn't really make sense, is going to be 1.87 seconds. So this is an important sort of intermediate step in this problem, because this will help us to sort of define these positions. Okay. All right. Now, with that information, we can just go ahead and calculate what our position is at this particular time. So our position r, given this time of 1.8 seconds, okay, well, I can just plug in here. My position r is 0.9 minus 0.12 times my time squared, which is 1.87 seconds squared. This will leave me with my position at the snapshot of time that I'm interested in, where theta is 30 degrees. Here is going to be 0.48 meters. I can do a similar thing to calculate what is sort of the velocity of the particle along the shaft at this particular time. That general expression here is negative 0.24 t, or negative 0.24. I'll actually plug in my time here. It's 1.87 seconds. This will leave me with sort of the velocity of the collar along the shaft at this very particular instant, negative 0.45 meters per second. Okay, so the collar is located at 0.48 meters, and it's moving towards the origin with a speed of 0.45 meters per second at this particular moment. Lastly, my acceleration is given by negative 0.24 meters per second squared. No time needed to be plugged in there, just we have it already. All right. So these are the variables that I'm going to end up using in my calculation of velocity and acceleration. But remember, I still also need theta dot and theta double dot terms. First, I will need them as a function of time, because I'm going to just take the time derivative of the expression theta. So theta dot is, remember, the time derivative of theta, which here is the time derivative of our expression for theta as a function of time, which is 0.15 t squared. So this is 0.30 t. And here, with taking the derivative, this will be radians per second. As a function of time, my angular acceleration, 0.30 radians per second squared. In the snapshot of time that I'm interested in, we're going to have theta dot is 0.30 times my time. Which here is 0.56 radians per second. And since theta double dot does not depend on time, it's going to be constant, 0.30 radians per second squared. Okay, so all of these bits of information happen to be the bits of information that I need to know at this particular snapshot in time. So my theta double dot, my theta dot, I have at this particular snapshot in time, what is R double dot, and what is R and R dot. So specifically at this particular time, right? And lastly, we know that the angle theta is 30 degrees at this particular snapshot in time. I have all of the pieces of information I need to actually go ahead and figure out what is my velocity and my acceleration at this particular snapshot in time. So finally, and now my velocity is given by the general expression r dot e hat r plus r theta dot e hat theta. This is my general expression for the velocity. I have all of this stuff. Okay, this is just plugging in information I've already figured out. R dot was negative 0.45 meters per second. My position R at this one snapshot in time is 0.48 meters. My angular velocity at this particular time, just theta dot, 0.56 radians per second. And this is in the theta direction. So after some math, we can get that our velocity, negative 0.45 e hat r, plus, sort of after doing the math on the right-hand side here, 0.27, sorry, e hat theta, units here, meters per second. All right, so there you go. There is the total velocity of the collar, or the velocity of the collar at that particular instant. If you're interested in the magnitude of the velocity, which you might be, you go about it in the same way that you would the magnitude of the velocity in rectangular components or with normal and tangential components. And that would be each one of these individual bits squared. And taking the square root. Units here still meters per second. So if you wanted to give sort of a magnitude of the velocity at this particular snapshot in time, that would just be 0.53 meters per second. So here are your sort of answers for this problem. If you're asked for the velocity vector, this would be your solution. If you're asked for the total magnitude of the velocity, which is, I think, what they're after here in this problem, that would be your solution. So that's part A. Okay, part B. We're asked for what is the acceleration. Okay, again, we have all of the bits and pieces to plug into our acceleration equation. So remember our acceleration equation. We have all of these sort of crazy terms, but each one of them, you know, we've talked about their physical interpretation or their physical meaning. Here we have r double dot minus r theta dot squared along e hat r. Okay, so your extensional acceleration here and your centripetal acceleration term here, plus what is our transverse e hat theta terms, which is going to be r theta double dot plus 2 r dot theta dot So remember here, this is like your angular acceleration term. And this is your Coriolis term. That's sort of weird mathy term. All this in E hat theta. All right. Time to enter our values. R double dot. Negative 0.24 meters per second squared. Minus R theta dot squared. So the position at this time is 0.48 meters. Times my angular velocity at this particular moment, which is 0.56 radians per second, all squared. Can't forget that square. Don't forget that square. Oh my gosh. E hat R. And I'm going to add to that my transverse terms. So here, R theta double dot. My position again, 0.48 meters. My angular acceleration, negative 0.24. Is it negative 0.24? Oh no, I'm confusing that with the positional acceleration. Here this is 0.30 radians per second squared. Plus this term here is 2r dot theta dot. R dot is sort of my extensional velocity, negative 0.45 meters per second. And my theta dot term, 0.56 radians per second. All this in E hat theta. Sort of ran out of room there a little bit. After sort of all the algebra settles and the dust settles, since basically you have all of these values, negative 0.39 E hat R minus 0.36 E hat theta meters per second squared. So there's your acceleration. Okay. You could get the magnitude if you wish. You could find that the magnitude of the acceleration here, negative 0.38, sort of makes sense. Is that right? That doesn't seem right. Ah, I made a boo-boo. Okay, 0.53 meters per second squared. Okay. So there you are, your velocity and acceleration terms. Pretty easy. You really have to consider, again, what is the radial position, the change in radial position, and the acceleration of the radial position at this particular time. So that is what is R dot, what is R double dot at this particular time. Also, what is my angle theta, what is the change in theta at this particular time, and what is the change in theta at this time. So what is theta, theta dot, theta double dot at this particular time. Once you have all those bits, it just basically becomes kind of plugging and chugging. All right, so there you go. I think I'll try to find some time this weekend to maybe do like one or two more of these example cylindrical coordinate problems. They tend to be sort of some of the trickier problems for students to sort of understand and wrap their heads around. So maybe I'll try to find some time to post one or two more videos on cylindrical coordinates and practice problems here. But this is a pretty good start. So thanks for coming. Thanks for watching to the end. If you did, good job. If you're sleeping, wake up. Thanks for coming. We'll see you next time.